Okay, so in this video, I want to discuss equivalent resistors. And maybe you remember, we did something very similar to this for capacitors. And I kind of had a rule of thumb for how to do this. And it's always the same. It's the same as it was for springs. It's the same for resistors and capacitors. And the statement is, find the quantity that adds and find the quantity that is the same, and then take the ratio of the thing that adds divided by the thing which is the same. And that's really where all the key to deriving all these kind of equivalent quantities, and it's the same process. All right, so now I'm going to apply that strategy to resistors. Change markers here, hopefully stay fresh. So let's start with something really simple. Let's start with resistors in series. Series means that I have a chain of them in connected along a single branch. Okay, so I can start at points A and B. And if the real way to define series is that if I were to cut one and only one wire, would it stop the flow? Would there be no flow at all? Parallel, it turns out, will still allow flow, whereas series will be stopped. So these are all in series, because if I were to cut the wire, then you would get no flow through any of them. Okay. Well, what do we know about voltage changes? We know that voltage drops just accumulate. So the voltage drop, if I said this was resistor 1 and R2 and R3, imagine there's a current flowing, then I would say that the total voltage drop is just the sum of all the separate ones. So I'd say V total is just V1 plus V2 plus V3. On the other hand, the current through this resistor is the same as the current through the second one, is the same as the current through the third one. The currents are all the same. So the total current is the same as the current through resistor 1, is the same as the current through resistor 2, is the same as the current through resistor 3. They're all the same. And my strategy for coming up with equivalent quantities is to take the thing which adds and divide it by the quantity which is the same, is constant. So taking that strategy for those resistors, I would say, okay, the total voltage drop divided by the total current equals the voltage drop through 1 plus the voltage drop through 2 plus the voltage drop through 3 divided by the total current. But since the total current is the same as the current through 1, is the same as the current through 2, same as the current through 3, I'm actually going to distribute this and write this as this divided by I1. And over here I'll write it as I2. Over here I'll write it as I3. Now these denominators are all the same, but I'm just writing it in a suggestive way. And what this is like is the following. It's like I had my resistors, 1, 2, 3, and it's kind of like I've just kind of shrink wrapped it with plastic and just viewed it as one giant object. And if I did that, then going back to my formula for resistance, remember V equals IR, I would see that V divided by I is nothing other than, I would call this thing the equivalent or total resistance, and that would equal R1 plus R2 plus R3. So this is the formula for resistors in series. Their total resistance is just the sum of all the separate resistances. Just add them up. Easy. Now we're going to do the same thing for resistors in parallel. When you have resistors in parallel, let's imagine we had 3 resistors in parallel. R1, R2, R3. So if I have 3 resistors in parallel, now, you know that the voltage can't change, or the potential doesn't change in the wire. So that means that all 3 have the same potential on one side, and they all have the same potential on the other side. That means that the differences in potential are the same for all 3. On the other hand, think about the flow of electricity. If you had current going in, I total, it would go in, and that charge would have to split. You know, some would go up, some would go down, whatever. And you would have current I1, you'd have current I2, and you'd have current I3. And the only thing we know is that I total equals I1 plus I2 plus I3. But they all have the same potential. Because they're in parallel. When things are in parallel, their potential drops are the same. When they're in series, the potential drops add up. Right? So in parallel, these are in parallel because if I cut one wire, I can cut any one of these wires and the electricity would still find some way through the circuit. So these are in these resistors are in parallel. As opposed to series. Okay, my strategy for combining these into some kind of overall effective resistor is to take the thing which adds and divide it by the thing which is constant. So if I do that, here's the thing that adds, and I divide it by V total, which of course is the same as V1, which is the same as V2, which is the same as V3. I learned that in parallel, 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. So when they're in parallel, you don't add the resistors, you actually add the reciprocals, and don't forget to take the one last reciprocal to get the left-hand side. What many people do is they remember to add the reciprocals on the right-hand side, and they forget to that gives you the inverse of the resistance, and you have to flip it one last time. Let's do an example and see what that does to things. Let's imagine that I had, some sort of a resistor and let's imagine I had 2 1-ohm resistors in parallel. Let's find the equivalent resistance. I would say 1 over R equivalent is 1 over 1 ohm plus 1 over 1 ohm equals 2 over 1 ohm. Therefore, R equivalent equals a half of an ohm. So notice what happens. When you put resistors in parallel, the overall resistance shrinks. When you put them in series, it grows. One way to think of it is think about water flow in a river. Basically, if you give something twice as many paths, then it's just going to be easier for water to flow through. And so by giving the electricity multiple paths, the effective resistance goes down. Okay. So that's how that will work. And that's generally true. In parallel, the resistance shrinks. In series, it will grow. We can do more complicated things as long as we work in steps. So let's take this following setup. Imagine I had a resistor going into a pair of resistors, which were in parallel, going into another resistor. And I'll say that this is 1 ohm. I'll say this is 2 ohms. I'll say this is, let's say this is 1 ohm. And we'll say this is 3 ohms. How would you do this? In total, this whole thing is not in series or parallel. It's just something complicated. However, if I do it in stages, it's okay. First thing I would do is kind of smush these together and view them as one equivalent resistor. So they're in parallel, so I add them together using the parallel formula. And after I replace the parallel bit with one object, I can smush them together and view them as resistors in series. So the first step would be to combine these. That's going to give me 1 over 2 plus 1 over 1 equals 3 halves, and it's inverse ohms. So therefore, this whole thing together is the same as 2/3 of an ohm. That's in the middle. So now I can replace, I can redraw the circuit here as 1 ohm, 2/3 ohms, 3 ohms. And combining those, common denominator 3, I have 9/3 plus 3/3 gives me 12/3 plus 2/3 gives me 14/3. So I get R equivalent equals 14/3 ohms. Okay? And in that way, you can sort of systematically simplify things by breaking them into little bits, little pieces which are separately parallel and series, and then you just kind of work your way through a circuit and you can build up ever more complicated examples. Okay, stop there.